These are the syllabus dot points that relate to the next section of the work. There are natural sources of sulfur dioxide and oxides of nitrogen, and there are also man-made ones, and they're largely industrial ones, and we'll be talking about those and the equations involved in reactions that lead to the release of the sulfur dioxide and release of the oxides of nitrogen. And this is a real phenomena. We will be showing that there's evidence for this, and there will be effects of this as well.
The chemicals that we release into our atmosphere have a wide-ranging effect on the natural world. Rivers like this one in the Peak District can be devastated by contamination. Chris Curtis of University College London has been monitoring pollution and its effects on the countryside.
I'm just going to test the pH of this drinking water. This is good old London tap water. For comparison with acid river water sample. And as you can see, when I put the probe in the tap water, the pH goes up to about 7, which is circumneutral. So that's neutral tap water. But if I then put the probe in the stream, the pH value goes down to about 5.2. Now, because that's a difference of 2 pH units, but because pH is a logarithmic scale, that actually means it's not 10 times, it's 100 times more acid in the stream than it is in the tap water.
Okay, he's kicking at the bottom of the pond in order to get the living organisms to go into the
collect the insects,
net.
Other invertebrate animals that live under the rocks and in the gravel to see which species are present and see whether there are any acid-sensitive species present, which might indicate that this system is recovering from acidification. And what we can see is that there's actually not very much here. That might seem like a bad thing, but it does tell us a lot about the stream, and it tells us that the water quality isn't very good. In other words, it's very acid. If we went to a very healthy lowland stream with a high pH, we might expect to find a very diverse community of invertebrates.
Look,
living
there's
in
an
the
invertebrate,
rocks in the stream.
but there aren't very many of them.
That they could have been killed by acid episodes in the stream.
Rob Mills from Bangor University uses a different technique to test acidity in the This water can also be tested using an ingenious collection.
Okay, what this is we call it the cloud collector, and essentially what it does is it collects clouds. So as the clouds move across the hillside, they come across this fishing line wire, and small droplets from the cloud condense on here, run down into the funnel, and we collect it at the bottom. And this is another way of us getting an idea on how much acid material is coming into the system. We can have a quick look at this. And what we can find in here is that this will be full of a range of particles. And these particles are what the water droplets condense around. So this could be particles of dust from car vehicle emissions, from fossil fuel power plant emissions. And each one of these tiny little specks of black dust could represent a single droplet. And of course this material then eventually enters the ecosystem, and the consequences of which we're trying to find out.
Another of Rob's tests assesses the effects of global warming. He covers sun plots at night in order to...
Okay, so acid can enter the environment by dissolving acidic oxides in water, and then that makes an acid rain deposit, or it can accumulate around particles like soot that are produced during combustion, and the solids that are suspended can either come down in the rain or they can form dry deposits, which are also very dangerous. Okay, now, so not all of these things are man-made. There are natural sources, and some of these natural sources include volcanic eruptions. There are large amounts of sulfur dioxide and oxides of nitrogen that come out of volcanic eruptions, and geysers. Geyser pools often smell quite strongly of sulfur because they're producing large amounts of sulfur dioxide. Bushfires release a lot of carbon dioxide and sulfur dioxide, and lightning provides a massive amount of energy so that the N2 and the O2 in the atmosphere that would not normally react actually go through reactions and produce nitrogen oxides. There are bacteria that produce a rotten egg smell, which is H2S or hydrogen sulfide, and that reacts to form sulfur dioxide as well. Now, you get different sources of acid rain, and this diagram shows it. Industrially, we burn off a lot of coal, and coal actually contains a certain amount of iron sulfide. It's another smelly substance, like smells like rotten eggs. And when you burn it, you get lots of sulfur dioxide, and that can react with the water and produce sulfurous acid, or it can react with ozone and make sulfuric acid. And in the same way, oxides of nitrogen can react with ozone in the atmosphere, and that will also produce nitric acid, and that will produce acidic deposits in the rain clouds, or it can attach itself onto the soot particles in the atmosphere, and then the soot and the rain come down as precipitates, as wet deposits, or sometimes just the soot can land and accumulate, and it's like crystals of acid that are coming down to burn. Now, notably, cars produce oxides of nitrogen as well in quite large amounts. So they tend to be a source of cars are more likely to produce lots of nitrogen oxides. Coal is more likely to produce higher amounts of sulfur oxides. And these are the equations that go with that. This is actually the part, a very, very small fraction of coal, but when it reacts, it will produce quite a lot of sulfur dioxide. And Australian coal actually does have quite high content of iron sulfide in it, and it means it's not good quality in the sense of having too much sulfur dioxide. The other process that we all know about is getting ores of copper and trying to smelt the ores of copper. And one of the processes is going to get rid of this sulfur here, and it will do it by reacting to produce sulfur dioxide. Of course, sulfur dioxide can react with O2 to make a sulfur trioxide, or with ozone, which is O3, to make sulfur trioxide and oxygen gas. This sulfur trioxide then, of course, can directly combine with water and make sulfuric acid. Okay, this part will actually be in the next section, so I'll show you that in the next section because we're running out of time.